Hello again. This is the Pencrest High School AP Physics C video series. This is video 3C, potential energy graphs. So what we see here is a graph of potential energy versus position. So we see energy in joules on the left axis and position in meters on the horizontal axis. The curving function that we see here is the potential energy based on the environment, based on the surroundings. The horizontal red line that you see at 32 joules is the total energy of the object in the system. We can assume for the purposes of these graphs that there's no work done on the system from outside. The location of the horizontal line would be determined by where the object is released and how fast it's moving, essentially how much kinetic energy it has. So we have a function here that is determined by effectively by the surroundings. So this tells us what the potential energy of any object would be based on its location, based on its horizontal position x. In this case, 2x cubed minus 14x squared plus 17x plus 20. The u of x obviously is in joules and x is, in this case, in meters. So the conservation of energy at any point in time says that the total energy in the system is equal to U plus K. So potential plus kinetic energy. If we think of the graph, the U of X graph, as actually a track, like a roller coaster track, this can tell us what the object does if it's released at a particular location with a velocity in a particular direction, or not, as the case may be. It can be released from rest. I want you to notice also that the energy axis has a 0, and the U of X graph actually goes below that. So this tells us that the potential energy can in fact be negative if it happens to be between this location here and this location here. The potential energy would actually be negative, and that's sort of arbitrarily chosen, that this elevation or this position indicates a potential energy of 0. Now, if we know the mass of the object, we can use this graph to determine U at any position, the kinetic energy K at any position, and if we know its mass, of course, the velocity at any location. We can also use this U of X function to determine the force on the object at any point, at any location X, using this formula that you see in the blue box here. The force on the object is equal to negative du of x over dx. So in other words, we take the derivative of the u function at that location, make it negative, and that will tell us the magnitude and the direction of the force on the object at that location. That negative sign is important. If we consider locations on this graph where the slope is negative, the derivative would be, the negative of the derivative would be positive and would indicate a force on the object to the right. If we see locations here where the U of X graph has a positive slope, that would indicate the negative derivative would be negative, and it would indicate a force that would be acting to the left. So if we look at the graph a little more closely, at this location here, so this happens to be 5.7 meters in this case. The U of x graph intersects the total energy. So in other words, all of the total mechanical energy is potential energy. This is what is called a turning point in the object's motion. Obviously, if the total energy equals U plus K and U equals E, that means the kinetic energy is 0. So the object stops there. And this becomes what's called a turning point. If the object is moving to the right and it reaches this point, it's going to stop and then come back to the left. Okay, so that's why it's called a turning point. The locations on this graph such that x is greater than that turning point, x is greater than 5.7 meters, are called forbidden. We have a rhetorical question here. Why would they be forbidden? As it turns out, in order to obey the conservation of energy law, if E equals U plus K, this location here would imply that the potential energy was greater than the total energy. That would imply a negative kinetic energy, which is, of course, impossible. So anywhere the U of x graph is above the total energy line, that would indicate positions that are forbidden or positions that the object will never reach. Okay, a couple other things here. If we look at the points where the graph changes direction, we've got one here at 0.717 meters. This is what's called a location of unstable equilibrium. Once again, if we put a ball there, right at 0.717 meters, it would sit there without moving in either direction. But if the object is disturbed from that location, it will then accelerate away. Could accelerate to the left, could accelerate to the right, but it's going to move away from that equilibrium position. Similarly, we have this other point here at 3.95 meters. This is a location of stable equilibrium. If we put a ball there, it'll sit there without moving. If we disturb it in either direction, if we disturb it to the right, it will go up the hill a little bit, then it'll come back. If we disturb it to the left, it'll go up this hill and come back. So this location is stable equilibrium. This location is unstable equilibrium. These equilibrium points are locations where the force on the object equals 0. And if we think about, once again, the slope of this U of x graph, at that location the slope is 0, and at this location the slope is 0. If we take the derivative of that U of x function, set it equal to, make it negative, and then set it equal to 0, solve the resulting quadratic, and that will tell us where those equilibrium points are. Now, if we were to release the object from rest at a position x equals 2 meters here, if we release the object from rest at that point, that effectively determines where the total energy line is. So E equals U plus K, and that means that once we release an object from rest at a particular location, that fixes the total energy at that level, where the total energy equals U at that point, because it's released from rest, so it's not moving. So the total energy line goes straight across from that location, and we can see that there are areas here and here where the positions are forbidden. So released from rest at x equals 2 meters, we see that the slope of this line is negative. That means that the net force on the object is to the right. Net force is positive to the right. This object would accelerate to the right from x equals 2 meters. It would accelerate to the right until it reached about here. Again, it says roughly 4 meters. We know already that's 3.95. The object would accelerate to the right until it got here. Then it would begin to slow down as it climbs up this side of the u of x graph. Again, if you picture a track of a roller coaster, put a little ball on it, the ball would accelerate down and to the right here, and then it would go up the well, and it would actually stop here at the other change of direction, the other turning point, and then it would begin to accelerate back to the left, down the well, and then up to the right, and it would stop here, and then back to the right, and up, and stop here, and it would go back and forth forever, right? So this is what's called a potential well. Given those conditions, releasing an object at rest, or from rest at 2 meters, the object would move back and forth in this potential well. Again, we're assuming no work is done, so no energy is added or lost. It would move back and forth inside this potential well forever. It's called a potential well because the object does not have enough energy to get out of the well. If we obviously, if we release the object from a particular location with some kinetic energy, then we would add the potential energy at that point plus the kinetic energy at that point to get the total energy in the system, and then that would determine where the horizontal total energy line went on the graph. Okay? So we'll be looking at a number of these. We'll have a daily, and we'll also have an individual u of x graph interpretation that you'll have to do. So that will be the that'll be the asynchronous Friday assignment. Okay, so next up is the work and kinetic energy principle. Until then, enjoy, and I'll see you again soon.